this is the last lecture of this week. Here we will see some numerical examples related to the laminate stiffness. First example says we have a laminate with stacking sequence minus 0, 60, 0, and this is under a uniaxial force Nx. So, the laminate stacking sequence is minus 0, 60, 0, and there are 3 layers: minus 60 degree, 0 degree, 60 degree. Now, there are 3 layers. So, the middle of the mid layer will cause consider as z equal to 0, and each ply is 0.2 millimeter thick. That means, from mid to here it is minus 0.1, from here it is 0.1 millimeter, and this one is again 0.2 millimeter. So, we can say at the bottom Z 0 is equal to minus 0.3 millimeter, Z 1 is equal to minus 0.1 millimeter, and this is equal to Z 2, and Z 3 is again 0.1 millimeter, and Z 4 is again 0.3 millimeter. And we have been given the material properties, and we need to find out the stresses in each ply. So, for that first we need the Q matrix in the material coordinate 1, 2 coordinate. So, for that we need to calculate nu 2 1 first. So, nu 2 1 we know is equal to E 2 multiplied by nu 1 2 by E 1. If we do that, then nu 2 1 comes out to be 0.0214. Now, we have to find out the Q matrix. So, Q matrix we know Q 1 1 is equal to E 1 divided by 1 minus nu 1 2 nu 2 1, and that gives us Q 1 1 as 140.9 GPa. Now, we have to find out Q 1 2. Q 1 2 is nu 2 1 E 1 or nu 1 2 E 2 by 1 minus nu 2 1 nu 1 to nu 2 1, and that gives us 3.02 GPa, and then we have, and this is also equal to Q 2 1, Q is symmetric matrix, and then we have Q 2 2 is equal to E 2 divided by 1 minus nu 1 to nu 2 1. Again we should correct this also 1 minus nu 1 to nu 2 1, and similarly here E 2 by 1 minus nu 1 to nu 2 1, and that is 10.06 GPa, and we have Q 6 6 that is equal to E 6, which is 6 GPa. So, this ply, the second ply, the mid layer has an orientation 0 degree. That means, it is an specially orthotropic ply, and its axis x coincides with axis 1 and axis 2 coincides with axis y. So, we have the Q matrix for a 0 degree ply in the xy system same as this Q matrix. So, 140.8, and then we have 3.02, then 0, 3.02, 10.06, 006, that is in GPa. The layer 1, first layer, that has a minus 60 degree orientation. Again, instead of writing the layer number, here we are just denoting the orientation. So, we have already discussed the equations which helps us transform this Q matrix into the XY system. So, using those equations, if we calculate the Q matrix with respect to the XY system, then what we get here is 20.1, 25.69 minus 15.24, and then we have 25.69, here we have 85.51, and then we have minus 41.1, and then we have again minus 15.24, minus 41.41, and here we have 28.67, and that is in GPa. And then accordingly, if we find out Q matrix for the XY system, we have 20.1, 25.69, 15.24, 25.69, 85.51, 41.41, 15.24, 41.41, 28.67 GPa. And this is obvious also, if we know this, we can find out this also. We know that when angle, I mean it is one is minus 60, one is 60. So, in that case this quantity, this quantity, this quantity, this quantity and this quantity remain same, and these two couplings are just change their sign, and that is what is happening here. Now, we have to find out A matrix, B matrix and D matrix. So, for A matrix, we know that the expression of A matrix is summation of k is equal to 1 to n, then we have Q matrix multiplied by zk minus zk minus 1, and this is quantity is nothing but thickness of the kth ply. So, if we do that, then what we get is here k is equal to 3, and this is xy for the kth layer. Now, for when k is equal to 1, this is k q minus 60 degree, and when k is equal to 0, this is q 0 degree. When q is equal to 3, then this is q 60 degree. Now, if we add up these contributions, finally the A matrix that we get is 36.22, 10.88, 0, then we have 10.88, 36.22, 0, 0, 0, 12.67 GPa millimeter. So, Q matrix that its unit was GPa, here we are multiplying thickness which is millimeter. So, it is GPa millimeter. Now, for the B matrix, again we know B matrix is k is equal to 1 to n, then we multiply qxy for the kth layer with zk square minus zk minus 1 square by 2, and then we sum up for all the layers. After we do this, what we get is 0, 0, then minus 1.22, 0, 0, minus 3.32, and then we have minus 1.22, minus 3.32 and 0, and this is GPa millimeter square, since we have z square terms here. Then we find out the D matrix. D matrix is K is equal to 1 to n Q with respect to x y for the kth layer multiplied by 1/3 of z cube minus z k minus 1 cube, and then if we again do it, we get 0.442, 0.4470, 0.447, 1.4820, 0.497 GPa millimeter cube. Now, this behavior of A matrix is also we can infer from what we learned in the last class. First of all, the mid layer has a 0 degree ply. So, that does not contribute to any of these couplings, any of these excess terms AXS or BXS or DXS or AXY, BXY, AYS, BYS or DYS. And then if we look at rest of the two layers, this one, the bottom one is minus 60 and top one is 60, and they are opposite of each other, and they are put at the two symmetric locations. So, that means these two gives the effect that we see in an antisymmetric ply. So, because of that also again these two couplings are absent here, and these two couplings are absent here. Here, although B matrix does not contribute anything, but we have seen that when two plies, angle plies are put in antisymmetric in an antisymmetric fashion. So, then these XS or YS terms in the B matrix, they becomes additive, and that gives non-zero contribution, and that is what we see here. Now, with these ABD matrices, we can find out the strengths, and from the strengths we can find out the stresses in each ply. So, if you want to find out the strengths, what we do is we write here we have Nx, that is the only force and there is no moment, and then we have A matrix which we have already calculated, B matrix and D matrix, and then we have epsilon x 0, epsilon y 0, epsilon s 0, kappa x, kappa y and kappa s. If we solve this, then we get these terms as, these strain components, the in plane terms and these kappa terms as this. After solving this, what we get is the following. So, these epsilon 0 terms are plus 00506, and then we have it is 306, and then we have minus 000568 and 0, and the first two terms in kappa are 0, last one is minus 3.8326. Now, these terms could have been found out using the compliance matrix also. So, I could have converted this AB, found out the compliance matrices small a, small b, small d using this ABD, and that would also from there also I could have found out this epsilon 0 and kappa terms. Now, what we do is we find out the stresses, but before that we have to find out the strengths. Now, these three components, they give the same contribution in stress, same contribution to stress for each of the plies. but for these quantities we have to multiply by z. So, accordingly we the contribution to stress would be different. So, what we do here is, if we look at each ply, z here is something and z here is something. That means, z here is different and z here is different from what is here. So, in between this the variation of strain is linear. So, what we will do is we will find out the stress at the mid of each layer. That is for the sake of simplicity. Ideally, we should find out the stress everywhere and we see how it is varying, but here just to keep it simple, let us find out the stresses at mid of each layer, that means here, here and here. So, this portion, the mid of the last layer, is at a distance 0.3 millimeter from the mid of the lamina. Similarly, the middle of this first layer was 0.3 from the lamina towards the negative direction, and the middle of the last layer is again 0.3 millimeter from the middle of the laminate, and that is a positive 0.3, and here it is just 0. So, if we find out the stresses at the last layer, first layer. So, before that let us just understand that these three quantities are these three quantities and these three quantities are these three quantities. So, this we will call it a vector epsilon 0 and this we will call it a vector kappa. So, the strain vector is equal to S, let us say at ply 1, strain is equal to epsilon plus z into kappa. Now, at ply 1, the mid of ply 1, we have z equal to minus 0.3 millimeter. So, we will write this minus 0.3 millimeter. So, let us write it like this in SI unit. Now, for that what we would do is we have written A, B and D in terms of GPa millimeter or GPa by millimeter or GPa or GPa millimeter. So, we can convert all of those to SI units, and whatever we find here we would use that. So, if we find out the stress finally, sigma x, sigma y and sigma s, that would be Q matrix for that layer, which is minus 60 degree multiplied by epsilon. And if we do that, the finally the stresses comes to be 29.4 minus 17.56 minus 8.4 MPa. And again, just to reinforce the fact that we need to be consistent with the units, otherwise the values can be different. I have used SI unit here in meter. So, for that better I convert all these things into SI unit and then we do the calculations. We could have used millimeter here and accordingly we could have put it in the proper unit. After that, at ply 2, z equal to 0. So, there is no contribution from the curvature term, because this quantity is 0 for that ply, and there we have sigma x, sigma y and sigma s as Q for 0 degree multiplied by this epsilon, which is equal to epsilon 0, because z equal to 0 there, and that value comes to be 42.95, 3.52, and we have 0 here. Now, this ply is a specially orthotropic ply. There is no coupling between normal and shear terms. So, we can see 0 here in the shear because there is no shear load, and at ply 3, that means at the top ply we have Z equal to 0.3. So, that would be epsilon 0 plus again 0.003. Again this quantities should be calculated based on the appropriate unit, and with that if we find out the stresses sigma x, sigma y, sigma s, and this is 90 degree, and if we multiply it by the corresponding epsilon, then the stresses that comes is 29.4. Then we have minus 17.56, and then we have minus 9.84 MPa. Again, because the angle here and angle here is opposite, and we know that the shear coupling is opposite of each other in those cases, and there is no shear load, only normal load. So, the only shear that comes is due to those couplings. That is why the shear stress here and shear stress here are opposite of each other. Now, let us look into the next problem. We have a laminate with stacking sequence 0, 90, 90, 0, and this is under the action of a uniaxial force Nx is equal to 100 kilonewton per meter. We have to find out the stresses in each ply. Each ply is 0.3 millimeter thick, and it has the following properties. So, properties are given here. So, we can see a symmetric laminate here with symmetric cross ply laminate. So, we have 0 degree here, 90 degree here, 90 degree here, 0 degree here. So, this we can call Z equal to 0. Here we have Z equal to minus 0.3 millimeter. Here we have Z equal to minus 0.6 millimeter. Then Z equal to 0.3 millimeter. At the top we have Z equal to 0.6 millimeter. So, here Q matrix is same as before. So, with respect to the principal material direction, we have Q matrix. For 0 degree we have 140.9, 3.02, 0, then 3.02, 10.06, 0, then 006 GPa. Now, if we look at 90 degree plies, the second and the third one, then just this Q22 and Q11 they change their position. I mean QXX is now Q22 and QYY is Q11, 006 GPa. So, with this now we can find out the A matrix. We know that A matrix is summation of these Q's multiplied by thickness of each ply. So, with that we get A matrix as 90.58, 3.62, 0, 3.62, 90.58, 0, 0, 0, 7.2, GPa millimeter. Now, we can write the relationship between the force resultant and the strain components. Here for the n vector we have only Nx, and this Nx is given to us, that is 100 kilonewton per meter. A matrix is known to us. We do not know these components epsilon x0, epsilon y0 and epsilon s0, and again since this is a symmetric matrix, symmetric laminate, so kappas won't be induced because of in plane forces. So only these epsilon zeros are there, and if we know a matrix, we know this n vector. So finally this epsilon 0 comes out to be 0.00110058. Epsilon y0 is minus 4.4244 into 10 to the power minus 5, and then we have epsilon s0 is equal to 0. Now there is no kappa, so this itself is epsilon x, epsilon y and epsilon s. So we have found out the epsilon vector. Now what we can do is we have to just multiply this epsilon vector with the q's of this each ply, and that will give us the stresses. So we have strain constant, but because the q matrix is different for the plies, we have to multiply these epsilons with the respective q, and that will give me the stresses in each ply. So we have here ply 1, then ply 2, and then here we have ply 3, and this is ply 4. Then we can write ply 1 and 4, the stresses would be sigma x, sigma y and sigma s. This is q of 0 degree ply multiplied by this same epsilon. Epsilon and epsilon 0 are same for this case, it does not matter because there is no kappa. So that gives a value of 155.68, and we have 2.89 and 0, that is in megapascal. And for ply 2 and 3, which are 90 degree plies, we have epsilon x, epsilon y and epsilon s as q for the 90 degree ply is equal to 90 degree ply multiplied by epsilon, and that gives a value of 10.99 minus 2.89 and 0. So, if I just plot the normal stress variation, it just looks like this and like this. So, this is layer 1, layer 2, layer 3, layer 4, this is 0 degree, this is 0 degree, 90 degree and 90 degree. So, in layer 0 degree layers have higher stiffness along direction 1. So, it gives us higher value of stress, and 90 degree layers have lower stiffness in direction 1. So, it gives us lower value of stress. So, with these two numerical examples, I would like to conclude this lecture here. Thank you.